Okay, so now on to some statistical physics. This is where we're actually worrying about the particles that are in a fluid, right? We have like some fluid or we have air and there's a bunch of particles in it, and we can actually figure something out about all of these particles that are bouncing around this box or in the atmosphere. And what we found was that the thermal kinetic energy in any dimension is 1/2 kBt. So if you know the temperature, so if right in here, if you know T, then you know average kinetic energy of any particle in there, right? So if you have a particle, so let's say you have you have some H2 in there, and you also have some O2 that's bouncing around in the same box where we have the same temperature, which one is going to be moving faster? Now, remember that O2, this is heavier, right? So which is faster? Well, to get the same energy, the one that's lighter, the H2, has to actually be moving faster. So the faster one is H2. Now, in 3 dimensions, so in 3 dimension, we have that the average kinetic energy is 3/2 kBt, and that's because in each dimension, right, we have, x, y, and z, and in each one of these dimensions, we have 1/2 kBt. So we're going to have one of those for each of these dimensions, and so just adding those up, you can add up the energy in each dimension, and so we get 3/2 kBt, average kinetic energy. So one thing, one note about this is let's take our H2 and let's just have it, sitting around. We have it in this box of air, and it's sort of bouncing around, and it's hitting other molecules, bouncing around. This is still our same H2, and so the average kinetic energy. So average kinetic energy here is going to be equal to 3/2 kBt. Now, what if instead what we did was we had a box, and in this box we put some water, and then we take an H2, and it's going to be a little bit denser, so but it's going to bounce around in here like this. Okay, so what's that going to be? So this is still the same H2 molecule that's bouncing around in here. So what is in here? What is the average kinetic energy for that H2? Well, you can use the exact same equation. It's still going to be 3/2 kBt as long as the temperature is the same. So that works independent of what fluid you're in. But keep in mind, given the weight of the particle, right over here, given the weight of the particle, you might have a different speed. Okay, so now we had the Boltzmann distribution, which you deal with when you have a particle that could say, let's say you have a molecule, and we talked about this a little bit in class. Let's say you have a molecule, and it could be, in this shape, or it could be in, I'm not going to be very, very good at drawing this, or it could be in this shape. And so, and let's say this has some energy U1 and some energy U2, and let's say U1 has that conformation of the molecule, right? So each of these is some sort of molecule. It's just made of atoms. And so U1 is greater than U2. Now my question for you is, if U1 is greater than U2, are there more particles or more molecules in which state? Well, you will always have that you'll have more molecules in this lower energy state. They always prefer the lower energy state. So you'll always have more in U2, but you can have them be equal if t is going to infinity. And so, let's start with this last fact and see how this last fact actually is related to our equation up here. And so, so let me just remind you of what this equation is. I know I just set up the situation and didn't quite describe the equation yet, but the equation is basically saying the probability of being in, this is the probability of being in which shape? This shape, and then this is now the probability of it being in this more kinked shape. Anyway, so is given basically by e to the minus u1 minus u2 over kBt. And remember, this is just giving you the ratios. So you can't, it doesn't tell you the magnitude of the number of particles. This is just the ratio here. So if we have, so one thing to note is if you have t going to infinity, then, so if this is infinity here, then we have e to the power 0, and so then this would go to so if t goes to infinity, then we'll have e to the 0, which equals to 1. So that means the probability for being in configuration 2 and the probability of being in configuration 1 is going to be equal, right? If they're equal, then we divide one by the other, and you just get 1. So that's the basic idea there. And then we went over this. We also went over this a little bit earlier.